So we've seen that the dot product can be written in this form. It's the magnitude of A times the magnitude of B times the cos of the angle between them. So that's really saying the length of A times the length of B in the direction of A. Now we've seen that just from the previous slide. Now that can be written as A1B1 plus A2B2 all the way up to ANBN. Now it's not wholly obvious that it can be written like that. I have a little derivation of that in the appendix section at the back of the course book, so you can have a look at that if you're unsure about it. Now I've also written out the Fourier series without the summation, just so we can get into each individual part of it. So that can be written as the A0 plus the A1 cos x plus A2 cos 2x and the B1 sin x plus B2 sin 2x all the way along to AN cos nx and BN sin nx. Now we've seen that we can think about the cos nx and the sin nx as forming an orthonormal basis. So we can think of that as the same as the vectors En hat, and we can think of the A0, An and Bn as forming scalar coefficients. So for example, we could write A2 cos 2x, that is equivalent to writing A2 E2 hat. So we can find the scalar coefficients by forming the dot product. That's the vector A dotted with En hat will give us the value of our coefficient An. But we no longer have two vectors. So for example, the previous vectors we were taking dot products of were E1 hat dot E2 hat. We've now got functions replacing the vectors. So now we'll have, say for example, cos 2x dotted with cos 2x. So let's call these functions and let's generalize it, and we'll call the functions f of x and g of x. So now what we have to do is we have to work out a dot product between two functions, f of x and g of x, such that it gives us the value a0, an and bn. So let's look at doing that now. So we're looking to form the dot product between two functions. Now what follows is a heuristic argument as to how we're going to do that. So we know that the dot product can be written as a1b1 plus a2b2. Now if we sum that up, it's the sum from n equals 1 to I of an bn. Now if we were to let n tend off to infinity, then we could say that this summation becomes an integral. And if these two vectors are now defined as functions, and we call the functions f of x and g of x, then we could make the argument that a possible dot product might be f of x dotted with g of x would equal the integral of f of x times g of x by dx. Now we could put in the limits as well of minus pi to pi, because we know that we're dealing here with the sinusoidal functions, and we know that the sin x and cos x repeat every 2 pi radians. So that is a heuristic argument, and it's a heuristic derivation of the dot product, and we're saying that this here is the dot product between two functions which we're looking for. But it's not the whole story, because we need to show that this dot product that we've formed here will actually provide us with an orthonormal basis whenever we're using the sines and cosines as the basis functions. So that is that we want to ensure that en hat dotted with en hat will equal 1, and the en hat dotted with em hat will equal 0. Now our EANs and our EMs here in this case are our basis vectors. Now our basis vectors are the value of A0, which in fact is 1, and it's the sin nx and cos nx. But of course we'll have to also check sin nx cos mx and cos nx cos nx and sin nx sin nx. So these are all the possibilities that we're going to have to check and make sure that this identity holds for. So we're wanting 1.1 to equal sin nx dot sin nx to equal cos nx dot cos nx to equal 1. And we want 1 dot sin nx equal 1 dot cos nx to equal cos mx cos nx to equal sin mx sin nx to equal cos mx sin nx to equal 0. Now, it's a bit of a mouthful that, and I think this becomes a bit more obvious whenever we work through and check and find out whether this dot product actually holds or not. So we'll do that in the next slide. So before we finish off here, we'll have to note that cos nx and sin nx form an orthonormal basis, but there's also another term. The other term is a coefficient of A0. So the coefficient of A0 is going to be a value of 1. Okay, so the full orthonormal basis is going to be made up of the value 1 and cos nx and sin nx. So we can see then that if we were to work through the first one here, so 1.1 would be the integral from minus pi to pi of 1 times 1, which is simply the value of x from pi to minus pi. So that would be pi minus minus pi, which would be 2 pi. Now we wanted that value actually to equal 1. So that's equivalent to having the orthonormal basis, for example, E1 dotted with E1. So two vectors lying across one another, which would be equivalent to just a value of 1. But we've got a value of 2 pi, so that's out by that factor, but that doesn't matter, we can deal with that in a minute. And we also wanted the sin nx sin nx to equal a value of 1, but it doesn't. It turns out it equals pi. And cos nx we wanted a value of 1, but it doesn't. It ends up equaling pi as well. And all the rest of them are equal to 0 as was required. Now I'm not going to sit down and go through the proofs of these. I've put them at the back of the course books in an appendix, and it's just really kind of bookwork. So now that we've found the dot product, we're going to have to deal with the fact that this one is equal to 2 pi when we wanted 1, and this was equal to pi when we wanted 1. Well, all we really need to do then is simply divide out by our 2 pi and divide out by our pi. So that means that whenever we want to work out the value of A0, then our dot product really then becomes 1 upon 2 pi times the integral from minus pi to pi of 1 times f of x. Now I've just left the 1 out because it's understood. So it's f of x, and that's going to give us our constant term A0. Also we can divide throughout by our 1 upon pi, divide out from by pi, that gives us 1 upon pi, the integral from minus pi to pi of our function f of x times g of x. Now that's going to give us our an's and our bn's. Now if we choose a value for our g of x being our cos nx and also secondly by our sin nx, then we can work out our value of an, which equal 1 upon pi times the integral from minus pi to pi of f of x cos nx dx, and our bn's will be given by 1 upon pi times the integral from minus pi to pi of f of x sin nx by dx. And we also get, as noted up here, our value a0, which is 1 upon 2 pi, the integral from minus pi to pi of f of x. So this here is the Fourier series, and this is a method that we employ in order to find the coefficients an, bn and a0. So this is what we've been working towards through the last 3 videos, and that's our final answer. Now what we're going to do is we'll take this and we'll work out the example of the square wave, and we'll find the values of our an's and bn's and our a0's, and we'll go back into the graphical calculator, we'll put those values in, and we'll see whether we're able to approximate that square function given these values of an, bn and a0. So there was quite a lot involved in that derivation, but it's worthwhile taking your time to work through it, and if you haven't seen it before, I'd imagine it seems quite strange and a bit difficult, and granted, the very first time I seen it, I had to really sit and think long and hard about it over a long period of time before I was able to really comprehend it and accept it. So just before we finish up, we just want to say this in words. We can approximate a function f of x by using a series of cosine and sine functions of varying amplitude and frequency components, which are integer multiples of a base or a fundamental frequency. In order to find out these values of the scalar coefficients a0, an and bn, we form a dot product. In order to get the an, the dot product with our function f of x is the integral from minus pi to pi of 1 upon pi times cos nx dx, and our dot product to find the sin nx is the 1 upon pi, the integral from minus pi to pi of the sin nx by dx. And again, the dot product to find the a0 is the integral from minus pi to pi of 1 upon 2 pi times the value of 1. So that's all there is for this video. In the next video, we'll go and we'll use this in order to approximate the square function, and we'll see that in the graphical calculator. So thank you for listening, and goodbye.